One of the most common misconceptions I've seen, even among experienced managers, is the belief that if a technique worked at one mining operation, it should work just as well somewhere else. However, the truth is, ground conditions can vary significantly, even between different areas of the same mine. That's why a geotechnical assessment is essential to determine the most appropriate method and make sure it meets a safe design standard. It is also why it's important to listen to geotechnical reasoning when they have concerns about any plans. Over the next 3 videos, we're going to explore how different rock types and load will influence the rock mass response in mining environments. We'll start today by looking at rock strength, then move on to some basic design principles, and follow with how mining-induced stress changes the environment. After that, we'll take a closer look at the different failure mechanisms we can expect to see underground and in surface mines. In mining, whether you're working underground or in surface mines, rocks behave differently depending on their properties and the forces they experience. One key factor that heavily influences ground response to mining activities is rock strength. Rock strength is related to the rock's composition, structure, and cohesion. Rock strength also impacts how a material behaves under load, and we typically describe that behavior as either ductile or brittle. Rock strength determines how much load, which includes stress from squeezing, stretching, or impact, a rock can handle, and whether its behavior to that load is ductile or brittle. This is important because soft rocks, which tend to be ductile, and hard rocks, which tend to have a brittle response, typically behave differently when you apply force. Ductile rocks tend to deform first before failing, while brittle rocks are more prone to higher loading without deformation before suddenly failing or fracturing.
So, ductile rocks initially absorb loads and respond by deforming gradually. They may bulge, compress, or stretch before eventually failing, but you will often see visible warning signs. Think of something like modeling clay. As you press down, it slowly spreads out. It doesn't immediately just break apart, it first deforms. That's ductile behavior. And it's typical of weaker or softer rock. For example, ductile rocks like clays, coal, or siltstone are soft and pliable, deforming under light loads in mining environments. Clays might squish slowly in a tunnel, coal could compress around a mine face, and siltstone may deform under stress, all producing faint rock noise like subtle vibrations. So, these rocks typically first start to deform under relatively low loads, gradually changing as they strain before failing. But they can't withstand much total load or stress before collapsing. So, a geotechnical design for soft rocks is likely to be very different to a design for hard rocks. Now compare that to brittle behavior, which is commonly seen in stronger rocks. Imagine a glass. You can load it up with weight and nothing happens until it suddenly shatters. It doesn't show visible deformation, but when it fails, it's abrupt and often violent. Brittle rocks crack, fracture, or shatter when the stress gets too high, creating sharp breaks or faults. That's brittle failure, which is common in hard, high-strength rocks. The key difference comes down to how rock types handle stress. Hard and typically brittle rocks resist deformation until they abruptly break. Although, of course, there are variations of rock types between these two extreme examples. Whether a rock behaves as ductile or brittle depends mostly on the rock strength and how quickly the force is applied. Here's another way to think about it. Imagine you're testing 2 beams, one made of soft pine wood, like the kind used in furniture, and the other of high-strength steel, like the girders holding up a highway bridge. When load is placed on the middle of each beam, the pine beam, being softer, starts to bend under just a little weight, like a sagging wooden plank. It flexes and deforms slowly, maybe creaking quietly as it bends. If you keep adding weight, it will eventually buckle or splinter, unable to handle much total load. This is how ductile rocks act in mines. However, the steel beam, being much stronger, stays rigid even as you pile on more weight. It holds firm, showing no sign of bending until the load gets too heavy. Then suddenly, it cracks or buckles with a loud snap like a bridge girder giving way. This is how brittle rocks can behave. They can withstand higher loads due to their strength, but when they hit their limit, they fracture abruptly, creating loud rock noise. The way each one fails tells us something about how they handle stress and load. And rocks aren't all that different.
The speed that force is applied to a rock mass also plays a role. Rapid loading, like from earthquakes, blasting or drilling, often triggers brittle failure in rocks, causing sharp fractures and loud rock noise, as the rock doesn't have time to deform smoothly. Slower forces, like gradual ground convergence or settling around new excavations, allows softer rocks to deform ductily, producing quieter, subtler noise as they deform. Although water in the rock's pores or fractures can amplify these effects. In soft rocks, it can make them more pliable, like wet clay, leading to smoother deformation. In hard rocks, it can reduce friction along cracks, making brittle fractures more likely. In mining, soft, ductile rocks might deform early under light loads, creating faint rock noise but failing sooner, which can lead to gradual slumps or tunnel squeezes. Hard, brittle rocks may resist higher loads, storing stress until they finally fracture or break, producing loud cracks or even dangerous rock bursts. These behaviors and their associated rock noise help geotechnical engineers predict hazards and design safer operations. Rock noise refers to the sounds of movement, cracking, or shifting within the rock mass. These can range from small-scale microfracturing to larger energy releases. It's an important early warning signal, but the way different rocks make noise under stress can vary dramatically. So if we now apply this concept to the type of rock noise we might hear in different underground environments, it helps us understand potential early warning signs of changing rock noises. Soft, ductile rock tends to make a lot of softer noise as it deforms. Why? Because it begins to yield and move early. That movement produces sounds like small pops, creaks, and cracks. So, while soft rock may deform gradually, it also tends to give us early auditory clues that something's changing. An example of this is in coal mines where rock noise tends to be common. But if that noise suddenly stops, it may mean that the rock is no longer able to deform and it's starting to lock up. Stress is beginning to accumulate in a more brittle, unstable way. That silence can be a precursor to a sudden failure, especially if the ground has stiffened or dried out. Of course, this doesn't happen all of the time. The key thing is to understand what is normal for your work environment and notice when changes happen.
In contrast, hard, brittle rock is often quiet, right up until the moment it fails. It tends to absorb stress without giving much warning. When failure does occur, it can be sudden and violent, producing sharp, high-energy bursts of sound, often accompanied by rock bursts or seismic events. This makes brittle ground inherently more difficult to manage, because the warning window is typically much shorter. That's where seismic monitoring systems come in. They can detect a subtle rock noise and help identify zones that may be changing, especially if those changes suggest a larger event could be building.
In summary, as you get to know your mining work environment, pay close attention to what is considered normal rock noise and how the ground tends to respond to mining activity. Does the rock deform gradually before failing, or do seismic events occur with little or no warning? Remember, you can always speak with the site geotechnical engineer to better understand the expected ground conditions. That insight can give you extra confidence in knowing what to look and listen for